so they're going to be held tighter. And if you look at the electronegativity of sodium versus potassium, we know that sodium is going to have a higher electronegativity, I think, because it's smaller, right? And the electronegativity is going to go down. So really, at a molecular level, what polarizability is the ability to move these electrons around when responding to some incoming electromagnetic radiation.
So basically, then broadening it out is really just the electron, like the bigger in radius or the more electrons an atom has, especially like the more valence electrons it has, the more polarizable it is. Is that correct?
So not necessarily more valence electrons, because these both have 8 valence electrons, right? Sodium 0 and potassium 0 metals, they have closed shell, right? They're going to have 8 valence electrons. So they have the same number of valence electrons because they're in the same row, but there's more electrons around potassium. It's bigger, right? So the polarizability will go up. I think if you look at the equation for polarizability in notes 1, all right, notes 2. Well, it's in there somewhere. We'll find the equation for polarizability maybe in lecture tomorrow. But you can justify it based on, well, let's take another example, right? CF versus CH. We know that F has high electronegativity, right? So whatever electrons are around this bond versus whatever electrons are around this bond, we know it's going to be easier to move these electrons around versus fluorine, because fluorine is highly electronegative, right? So it holds onto those electrons tightly. So this is less polarizable, more so this whole polarizability thing really depends on thinking about what the electrons are doing, how tightly they're held, how big the molecule is. Does that clear things up a little?
Yes.
Okay. Think about it tonight and ask questions tomorrow. Yeah?
So the polarizability is inversely related to the electronegativity?
Yeah, for a given size. So you need to keep in mind the size of these things. So, but yeah, that's a good relationship to remember. So if you compare an easy one like right, electronegativity is very high for fluorine gas, and so it's very low polarizability because it's really holding on to those electrons. It's also very small, right, compared to bromine. And so bromine's polarizability is high. Which one has higher van der Waals forces? Bromine does, right? What are the forces in bromine? If it's highly polarizable, what are the different van der Waals forces? Name a couple of them. Dispersion forces, right? That's always a right answer because everything. Which else? Induced dipole, induced dipole. Any others? What's that? Is bromine a dipole? Nope. No dipole, dipole, right? So it's got dispersion forces and induced dipole. They both have, theoretically, dispersion forces and induced dipole. Although we might see something like C induced versus C dispersion, right? In our table, we might have something like this. -2, and we might have 10 and 14, something like that. So fluorine could have induced dipole, but when we look at the chart, it says no because it's so electronegative. So induced dipole is okay as long as I don't give you the chart. But if I give you a chart, you can tell me exactly which molecule has which forces based on the magnitude of these. These are maybe negative. Sorry about that. There you go. Does everyone get that? Okay, remember the chart's going to be important, right? So if you look at the chart or something like this chart. So if you look at this in lecture 3, and you figure out how to blow this up. Okay, so for methane, which is the top line right here that you guys can't see, but for methane, it's got induced interactions of 0, right? It's got orientational interactions of 0 as well. Why does methane have orientational interactions of 0? It's not a dipole, right? There's orientational interactions only occur between two permanent dipoles. So water and water, there's orientational interactions. Water and methane, there's no orientational interactions. And then everything has dispersion here. So, let's see if I give you are there induced interactions for oxygen? Probably. Are there induced interactions for nitrogen? Probably. Is the number higher or lower than for oxygen? Lower. More negative, right? -5. What about if I told you, are there dispersed interactions for oxygen? Yes. What's the number for nitrogen? Higher or lower? More negative, right? Why? So nitrogen, oxygen, nitrogen. Is nitrogen more or less electronegative than oxygen? Less, I think, right? So this is, I heard more electrons. I think that's right. It's also more polarizable. Right? So it's got higher induced forces, and it's probably it's larger, so it's got higher dispersion forces, right? What about boiling points? Which one has a higher boiling point? Nitrogen. And we know that this one also has higher van der Waals interactions. All these go together, right? So we see higher van der Waals interactions right from here. We know that molecule is more polarizable. It's got a higher boiling point. All of that stuff. Yeah?
Wait, those forces are more because oxygen has higher electronegativity?
So yeah, so this is higher. Higher electronegativity, right? And I think, let's get a periodic table up here so I don't confuse myself. Oh. Give me a tab. Okay, so nitrogen's right here, right? Oxygen's right here. So oxygen has more electrons than nitrogen, but it's also more electronegative. So it holds on to the electrons more tightly, and so that's why it's got lower induced interactions. Go ahead.
How does Born energy relate to how?
Oh, okay, hold on one sec. Is everyone cool on this? How electronegativity, polarizability, van der Waals forces, how all that stuff works? Okay, now you can ask your question.
Does higher self in Born energy mean it's easier to dissolve in a medium?
Yeah, so when we talk about higher or lower, we really need to quantify whether we mean more negative, more positive. You could say lower is more negative, right? Or lower is lower in magnitude. So there's two different ways to talk about that. So let's just talk about more negative. So if we go to, where's lecture 4? There we go. Let me save this. Okay. So we know that the Born energy is going to be inversely related to the dielectric constant, right? And the Born energy or the self energy has something to do with producing an ion in some sort of dielectric medium, right? And so we know that the Born energy is going to be proportional to 1 over kd. So as dielectric constant goes up, Born energy is going to get smaller in magnitude, right? So as kd goes up, delta W goes down in magnitude. And so there's less, if we want to create this charge in water, we have less self-energy than if we want to create this charge in a vacuum, right? Because just this relationship with dielectric constant. Okay, so we sort of get how, based on the equation, how Born energy varies with dielectric constant, but why do we care? The best way to explain this is to think about solubility in terms of transferring an ion from one dielectric constant to the other dielectric constant. So you can think about solubility as you start with, well, let's see. So you start with some compound, right? So let's say it's